Okay, good afternoon to everybody. Today we'll start a new part of differential equations. Actually, physical application. That means application of ordinary differential equations and or modeling with first order differential equations. So uh, we will solve the problem related growth and decay rate, finding growth or and decay rate. Okay, finding growth and decay rate with an initial value problem like this. The initial value problem. Initial value problem. That means the differential equations which is assigned with the initial values of the independent variables. Then we can take as an initial value problem like this. Suppose dx by dt with respect to time. Time is t is the independent variable and x is the dependent variable here. Suppose this is a differential equation. So x is changing with respect to time. Okay, x is changing with respect to time. Then this is the differential equations of first order and first degree. And we have assigned an initial value. If t equal to 0, then x equals to what? If t equals to 0, then x equals to suppose x naught. These types of differential equation is called initial value problem. Okay, where k is any constant, and we can solve this. Suppose x equals to, the solution will be like this. Solution equals to x is the dependent variable here. X is the dependent variable and t is the independent variable. So the solution can be written as solution can be written as like this, k into x naught into e to the power kt. This is the solution for this, because at if t equals to t naught, initial value t naught, then x equals to what will be x naught. So assigning these types of initial conditions, we can find this solution. X equals to what? X. So now we'll try to solve the problem like this for finding the decay, growth and decay rate. Okay, for finding the growth and decay rate. We'll try to solve this problem today. So application of differential equation in mathematical modeling. That means modeling with first order differential equations. Finding growth and decay rate. So first problem is the population of a town grows at a rate proportional to the population present at time t. Okay, the initial population of 500 increases by 15% in 10 years. Okay, to find the population growth, we can use the differential equations. Okay, so what will be the population in 30 years? How fast is the population growing at t equals to 30? That means 30 years. Okay, so time t is for time, and time is the independent variable here. So using this concept, we can solve the problem. First problem. So solution for the first example, I have shown you. So let y be the population at time t years, and y not be the population at time t equals to 0, and y not be the population at time t equals to 0. So we can form the differential equation like this. Then dy dt equals to ky, or we can separate the variable here, y equals to k dt. That means solving by variable separable method, we can solve here ln y equals to kt plus c. That means we can get the solution y c into e to the power what, kt. Okay, from this ln y equals to ln e to the power kt, and here it will be ln. Okay, ln. Then from this we can write this is the solution. Okay, so here imposing the initial conditions at t equals to 0. That means at t equals to 0, that means y 0 equals to what will be, y 0 equals to, if you put t equals to 0 here, we get y 0 equals to what, only c. Okay, from equation 1. So we see that y equals to initially how many populations, c equals to what, initially 500 e to the power kt, because initially we have population y equals to 5, 500. This is why y t naught at time t equals to 0, population what was 500. Okay, 500 equals to c. Therefore, c equals to 500. Just putting the values of c in equation 1. Okay, putting the value of c in 1, we get what, this one. Since this is equation number 2, since 15% of 500 equal to what, of 500 equals to what, maybe 75. That means 15 by 100, 100 and 500 will be cut. So 5 and 15 what, 75. Then in that case, y, therefore at time t, yt equals to, that means at time 15 years. Okay, time t equals to what was 15, sorry, 10 years, 10 years in question, 10 years. 10 years equals to what, 75. So 15% increase plus 500 equals to what was 575. So therefore equation 2 becomes 575, just putting the values of y. 500 e to the power kt. Now solving for k, we get solving for e to the power kt equals to what will be 575 divided by 500. Therefore, taking ln on both sides, kt equals to ln 575 divided by 500. Therefore, and t equals to what was t equals to actually 10 years. This is why we can put 10k. Okay. So k equals to 1 by 10 ln 575 divided by 500. So approximately k values will be 1 by 10 ln 1.15. Now, when t equals to 30, when t equals to 30 years, y30 from equation 1, y30 will be what? 500. This is the 500 e to the power k values into 30. Okay, e to the power k 30, but 500 e to the power 1 by 10 ln 1.15 into 30. Just using calculator, you can get these values. 500 e to the power 3 ln 1.15. Using scientific calculator, we can get 760 760 760 population. Okay, now differentiating, we get differentiating y dash or dy dt. The rate will be what? The rate will be k into, just from the original equation, k into what? Y to the 30 years. Y30. This will be Y30. Values, k values 1 by 10 ln 1.15 Y30 what? Y30 760 equals to 10.62. This is the result. So here the initial population was 500 at time t equals to 0 years. So we form the differential equations dy dt. Then after solving, we get y equals to constant c into e to the power kt. Now at time t equals to 0, imposing this condition, we can find the constant. Okay, constant value c equals to what? 500. Just putting this c equals to 500 in equation 1, we get equation number 2. Now 15% of 500 population increases, so increase what's 75. So total population what will be at time after 10 years? Population will be 500 plus 75. This means 575. Now after 10 years, from equation number 2, after 10 years, y value what? 575 and 500 into e to the power k into 10. Just from here, we get the value of k. Okay. Now at time t equals to 30 years, what will be the total population? 760. Okay. Just putting the value of k here. Now the rate of change of population within 30 years, just from here, we get these values. From here, this equation we got. Okay, the rate, this is the rate. Okay, this is the main differential equation. So y dash, that means dy dt at 30 years, k into y30. Okay, y30 means total population at 30 after 30 years, 760, and just my value of k will be multiplied with this. So the rate is what? 10.62. So this is the actually for the growth rate, for the finding growth rate, this is the modeling of differential equations of first order and first degree. So now the second example is the population of a bacteria in a culture grows at rate proportional to the number of bacteria present at time t. Okay, after 3 hours, it is observed that 400 bacteria present, and after 10 hours, 2000 bacteria present. So what was the initial number of bacteria? Now the solution for the second example. Let y be the bacteria population at time t years, and y not be the population at time t equals to 0. So same the differential, the rate of change of bacteria can be denoted by this differential equation dy dt equals to kt. So after solving, we can write y equals to what? Y equals to c into e to the power kt. Okay. Now at after 3 hours, the number of bacteria changed. How many? 400. Okay. So this can be denoted by yt. Remember it. Yt equals to this. So if t equals to 3 hours, then y3 equals to what will be? Y3 equals to 400 bacteria. Okay. So after 10 hours and after 10 hours, what's the number of bacteria? New number will be 2000. Remember it. This is given in question. So from equation 1, this is the exact general solution. So y equals to what will be? So from these two, we can write so 400 equals to what will be? 400, this from equation 1, 400 equals to c into e to the power k thrice k. Okay, t equals to 3 hours. T equals to 3 hours. This is why. So from here we can find the value of EK. From here, the value of EK what will be? (400) EK equals to 400 divided by 400 divided by what? C to the power 3K. Okay, to the power 3K equals to this value. Again, 2000 equals to what? Y10. Okay, C into e to the power 10K. E to the power 10K. So this equals to can be written as C into e to the power 10K means can be written as what? So from equation 1, at time t equals to 3 hours, we get the population, bacteria population 400 C into e to the power 3 thrice k. So e to the power thrice k equals to 400 by C. Now again from after 10 hours, 2000 bacteria population. So from this part, 2000 equals to C into e to the power 10K, but e to the power 10K can be written as 10 by 3 into 3K. Okay, 3 will be cancelled, 10K. So just using this, we have arranging. So e to the power 3K into 10 by 3. Now putting the values of e to the power 3K. Okay, this is equation number 2. So by equation 2, okay, by equation 2, we can write 400 by C e to the power 3K. Now only we can solve this only for C. So C value will be what? Like this, C to the power minus 7 by 3. So C equals to 2000 divided by 400 to the power 10 by 3. Power will be inverse of this. That means minus 3 by 7. And it is can be calculated by using scientific calculator. Okay. So using this scientific calculator, we can get the approximately number of bacteria to the 201. That means at time t equals to 0 from equation 1, from equation 1 at time t equals to 0, that means yt equals to initial number of population of bacteria. So c into e to the power 0k. E to the power 0 means what? 1. So on equals to what? C. And c value what? 201. So this is the actually result, initial number of bacteria population. Okay. Okay, now another example. That means for finding the decay rate. In example 1 and 2, we had used the modeling for first order and first degree differential equations for finding the growth rate. Okay. Now example 3, this is for finding decay rate. Initially 100 milligram of a radioactive substance was present. After 6 hours, the mass had decreased by 3%. If the rate of decay is proportional to the amount of the substance present at time t, find the amount of remaining after 24 hours. Determine the half-life of the radioactive substance. That means you have to find out the half-life, and you have to also find the amount of remaining after 24 hours. So for finding the decay rate, we are using the differential equations for physical modeling, really physical application. So for the solution of the example 3, we are using the same procedure. Let y equals to, let y t or y equals y will be the amount of the radioactive present at time t. So the rate will be, decay rate will be, can be represented as, and why not be the amount after decreasing at initial will be time t equals to 0. So decay rate can be represented as these by using these differential equations. T will be, time will be independent and y will be dependent. That means amount. So the decay rate can be represented by these differential equations. So dy dt equals to kt. And after solving, we can write this equation, differential equation, y equals to c into e to the power kt. Okay, this is equation number 1. Now, at time t equals to 0, at initial time, the amount of radioactive substance is what? At time t equals to y not equals to what? 100 milligram. Okay, 100 milligram. So from equation 1, 100 milligram equals to c into e to the power kt, means what? 0. Okay, c into e to the power 0, that means equals to c. Therefore c equals to what? 100. Putting the value of c in equation 1, that means y equals to 100 e to the power 30. This is equation number 2. Again, after 6 hours, after 6 hours, 3% decreases. Okay, decreases. So yt, therefore yt equal y3 equals to what will be? Sorry, y6 equals to what will be? 97. 3% decreases, and that means 97 remaining. Okay, so y6 equals to 97. That therefore from equation 1, 97 equals to, from 1, 97 equals to c into e to the power k 6. This equals to c value what? 100 e to the power 6k. From here we get the value of k. E to the power 6k equals to 97 by 100. So from here we get the value of k. K equals to what will be? 1 by 6 ln 0.97. Okay, approximately we get the value of k here. Now after 20 hours, 24 hours. Now after 24 hours, y24 equals to, from same equation 1, what will be? C into e to the power k t. 24 hours. C values what? 100. And k values what? 1 by 6 ln 0.97 into 24. So using scientific calculator, here we get 100 100 into 0.97 to the power 4, which is approximately 55.5 maybe. So after 24 hours, the amount of the radioactive substance equals to what? 88, approximately 88.5 milligram. Okay. Now, second part. Let T half equals to half life. We have to find out the half life. So at T half, the amount of substance, what will be? Reduced to half. Okay, that means amount was what? 100. Okay, 100. So at T half, amount will be what? Amount will become 50, right? So from equation 1, then from 1, y T half equals to C into e to the power k T half. T half is the half life, remember it. Or T half, y T half means what? 50. Amount 50, and C equals to what? C equals to 100 e to the power k. K value what? K value 1 by 6 k T half. Okay. So from this equation, 50 equals to 100 e to the power k means what? 1 by 6 ln 1 by 6 ln 0.97. Okay, and T half, we have to find out the value T half. So from this line, we can find T equals to what will be? T half equals to 50 by 100 means what? Half. Okay, half divided by this one, e to the power 1 by 6 into 1 by 6 ln half. This will be not only half ln, taking ln on both sides, we get 1 by 6, 1 by 6 into ln 0.97. Okay, so this equals to what will be? We get a approximate value. T half will be 136.5, maybe 136.5 hours. So the half life for the radioactive will be radioactive substance will be what? 136.5 hours. So very interesting example for finding the growth and decay rate for the modeling of first order and first degree differential equation.